Alright everyone, howdy, how's everyone doing? Alright, let me do this. Visualizer, there we go, initialize. Oh, there we go. How's everyone doing? By popular request, I will be doing a EE361 video for you guys on the Generalized Fourier Series, so hopefully this will be a helpful thing. Let me see if I'm recording. Hello. Yeah, it looks like it's recording. Hopefully the music at the beginning was. Yeah, we'll find out later. But point is, I'm gonna make this a short and sweet video to hopefully help you guys. So suppose we had some function, let's say f of t, which is equal to, I don't know, some complex thingy where it probably looks like this. Like maybe it's like some wiggle or something like that. Like some function you're like, oh gosh, what do we do with it? Or our computers just can't process this. Well, what if we can make this function out of, wait, let me just turn this on. Ah, that's better. We can destroy this or find out how many signals we can make out of a couple other functions, like really small ones, like f of, oh, this is a bad marker. Oh, it still works. F of like t to the 0, f1, f2, t is equal to t minus 1. And then we can just add a whole bunch of functions. Let's call it projection of t. It's basically a summation of other functions, f1 plus f2 dot 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 f of n. There we go. Oh, my microphone. There we go. So a simple function like this right here, t to the 0, this is actually just equal to, well, 1. That's a DC term if you want to think about it. This right here, t to the 1, well, you already know what that looks like. That just looks like a straight line like that, and on to whatever you want. So this is easy to calculate on a piece of paper or using MATLAB. We're trying to assume that we don't know how to create this, or maybe we're given some unknown signal and we want to create this unknown signal with signals that we know. So what I wanted to show you, and I'll probably use your assignment a little too. What's your first assignment say? Or the second one? I didn't do a first one because I was like, yeah, do I need it? And then everyone was like, oh, David, we miss you. I was like, you did? I thought I was hard. No, you're easy. I was like, oh gosh. Nah, just kidding. Most of this, I've already read through this. It's not that bad, just simple vectors. Oh yeah, you need to know what this is because you'll do it. Everyone's going to be doing this on their assignment. I think that's the solution. That one's going to be your alpha. That's your Gramian, your big square, and I think that's going to be that's your big square. No. This square right here, that's your bases or your Gramian. That is this, and then your functions, f of whatever. Actually, let me show you what I'm talking about. So actually, no, that's down here. Actually, no, I'll show you right here. So you already know your bases, and he does a script b, I think, times some alpha, which is equal to, well, the dot product of your function times b1 or 0, f of f dot b1 dot 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 f dot b of n. I think this is n minus 1 because you have 1, 2, 3, n minus 1 elements, or n elements, sorry. So if you had 3 signals, 1, 2, 3, that means n has to be 3 minus, this is, you know what I mean, right? But point is, if you want to solve for the thing we're trying to do, and I'll show you what I'm trying to do. Look at this example right here. Our projection is, I'll just call it proj of t, which is basically equal to f of 1, our function 1, times some weight. This right here, I'm just going to call it some weight. And I'll show you an example too. Like this is like, okay, how much of this function do we need? And then how much of this? And we're just adding them all. So times alpha 1, or I'll just keep numbers consistent, plus f of 1t times alpha of 1 dot 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 f of n minus 1 t times alpha n minus 1. So these right here, this right here is our basis functions, or whatever signals we want to use. Like this right here is our basis signal. I think that's what it's calling it. And right now, for practical engineering purposes, this is right here is like a weight, our weight of this function. So we have a whole bunch of these guys. You'll probably see this in your first your second example. The first example, let me show you that. Where is it? There it is. Sorry. Let's go over this. I checked this one. This is correct. This is another way of integrating, so use this as your advantage. And oh, you'll definitely need this to do multiple integrals of these. So use this code. This is all valid. I checked it. You already know from 360 how to plot analog signals. And so here is our little square. So the first example is going to ask you to, without using MATLAB, so you must do this by a piece of paper. This is why Dr. Stewart makes you do hand calcs, to derive the Gramian. And I'll show you how to do maybe just 1 point. So actually, let me just label this. Actually, can I do it on one piece of paper? So actually, what is the example asking? He gives you this. That's t of n from 0 to t. That's the time. And then however many basis functions you have. So t0, t1, dot dot dot, tn minus 1. So we're just going to do it for like this. And you'll have to do this on your exam. If you don't do this on your exam, you'd be sad. So our basis function, I'm just going to call it basis of n, lowercase is t of n. There we go. And we want to do this, b of 0, b of 0, and then b of 1, b, or 0, 1, dot dot dot, and then b of 1, b of 0, b of 1, b of 1. And then you see this diagonal right there. You can probably continue that on if you know what's going on. Like dot dot dot, dot dot dot, dot dot dot. But we're just going to solve for this. So I'll show you a really quick example to hopefully get you guys going, and then maybe help you with a little bit of the MATLAB of what you should be doing. So for b of 0, that's equal to t of 0, which is just equal to 1. So therefore, b of 0 is equal to, the rule is if you have two signals, you have to integrate given a time from 0, t is equal to 0, t is equal to 1 of this times this, but that's just 1. So 1 times 1 dt, which is equal to, well, 1. It's just a square. So that's 1. So now if we have the following, b of 0, b of 1 is equal to the integral of 0 to 1 of b of 0 is 1, and b of 1 is t to the 1 power. And you already know what the integral of t is. It's basically t squared over 2 from 0 to 1, but you already know that's going to be 1. So if you, okay, just for cleanliness, 0 to 1, you can do this math in your head, and that's going to equal to 0.5. Okay, you see the pattern? And it keeps going on, and you can multiply. Okay, maybe I'll show you this one. Maybe if you guys are confused. 1, b of 1, right? So you know you have these two basis sets. I'll write it down. You have to do this for your Gramian, okay? So you know this is going to be t to the 1 power, right? T to the 1 power, right? Okay, so you're going to do the integral 0 to t is equal to 1. just do that for cleanliness, of t times t, okay, these two, dt, okay, and you know this is going to be, do I want to skip steps? No, let's show you the work so that you know what's going on. 0 to 1 of t squared dt, okay, now you know what that point is, which is equal to t to 3, and do I really have to show you this? Yes. All right. And this is equal to 0.333. And you're going to be doing this, but don't do it, well, unless you want to. Let me show you this. So you have to, so this is without using MATLAB. So if you can do this by hand, you understand the assignment, you know what's going on, and hint, hint, if you do this on the exam, you'll be golden. So, but he wants it in terms of capital N, so you can figure out how to do that and be like, oh, b of n minus 1, b of n minus 1, and that's your last point. You know that's your last point, so that's how you do number 1. So now you're like, oh, you see a pattern, right? Actually, let me just finish the square. All right, so the first position is going to be 1, and then the next one is going to be 0.5. But knowing from symmetry, let me show you this. Here's our original square, right? That's our original square, right? So you have this term right here, and you have this term right here. These two are the same thing based on their operational thingies. I forget what the definitions are, but they're the same thing. You have b1 dot b0 and b0 dot b1. They're the same. They're linear. So that means this is going to be 0.5, and then this is 0.3, and then you can continue the pattern down to whatever number you like. This would be right here. There. So now you know how to do that, but I think he wants this in terms of n, or I don't know. So now you know that, and you're like, oh gosh, David, I know what's going on. I'm like, okay, that's great. So I'll show you this example in a bit. But so one of the functions he wants you to use is Hilb, and the Hilbert, if you're confused just like me, just do help Hilb, okay? MATLAB will help you. And it says, oh, it just it does this, a famous example of a badly conditioned matrix. I think Dr. Stuber talked about how it's like good, but it's like but if you're like confused like me and you're like, I don't know, man, Hilb of 3 or 2. All right, and if we enter that, oh, hey, whoa, what's this? Oh, 1. Oh, wait, let's do this. Hey, that looks like our Gramian. Now you know what to do. So, oh, look at that. That's your Gramian. You can put it into something, I don't know, call it my Gramian. How do you spell it? Gramian. There's 2 M's. There you go. So now you know that square. And then you're like saying, okay, David, how do I do the other stuff? I'll let you solve that on your own. But you'll see in the assignment, you know how to solve for that now in MATLAB. You want this. This is your weights. These are the things that, well, set this. And then all you got to do for this one is, well, I think this should be a really straightforward assignment. That's why I was asking, why am I even doing this video? But you guys should be fine, which is whatever your function is. Here it is. Let me see. Here's your function, like f of t is equal to exponent of t. You're going to plot this in the time domain, as you can see from here. Oh, here it is. That is our unknown signal. This is our unknown. That's our unknown signal. Okay. And you need to dot product this with, well, your first basis function, 0. And you already know how to do that, which is basically from 0 to 1 of the function itself, e of t, times, well, t of 0, dt. And you just do this all the way down the street and you'll get your numbers. Now that you have that function, but I need to show you something very important. You see how this is a matrix? Keep it as a matrix. So you see how it's this and this number right here. You'll have a time in there, but keep it like this, because then when you do this, where is it? This right here is literally your solution, I think. Where is it? This is gonna be your alpha is equal to your Gramian, and then this backslash thingy, and then whatever your function was. So it's gonna be very clean. If you're not doing this, then you're doing something weird, or please check with your friends. So that should be really easy to execute. But now I want to show you my example, to the whole point of all this. And I created here's your solutions. Just kidding, now just use that for review. So I created this. Let me run the section. Boom. Hopefully it does what I want it to do. All right, so let me get rid of the 3. Maybe that'll come in handy later on. So what I did right here is wait, no, that's bad. There we go. So I plotted these 3 functions right here. So here's our function 0, t0, 1, and 2. And you're like, okay, so I plotted all 3 of them. Here's 1. You can see it there. It's t0, here's t1, and here's t2, right? The whole point of this assignment is you're trying to find some weights, and I'll show you. I'll put this on the side. Put that right here. The camera, you can stay there. It's not bothering me, unless it does. You can see my hand though. We're trying to find a weight, and I'll put this as like 0.1. Oh, this. There we go. Boom, boom, boom. And all we're doing is just doing the following. Oh, aha, and that's why I have this 3rd one. Okay, let me show you what I'm trying to do. 1. I'll just do this for this shorthand. There we go. Same functions. So what I did right here, this figure 2, I just summed all these functions, right? The sum of all these functions to give me my projection. So this right here should equal some unknown signal. So this right here is my unknown signal. I just added all these 3. But if you wanted to know some crazy properties, I think you might have a negative number. Would you? I don't know. And we'll figure it out. But point is, these weights right here, 0.1, if you look at this, watch this. Like now you can see it change. Let's get rid of that. That's our original functions. And you can see it move a little bit. 0.1 and 0.05, I guess. See, now it changes a bit, but what happens if you have a negative number? Maybe you might see, oh, you see that? With these 3 functions, and maybe a negative number might pop out. I don't know. I don't remember. You can get a lot of cool, unique signals. So that's the whole point of these generalized Fourier series. You can use some weird basis signals, and you can create a whole bunch of weird random signals too. This right here, if you notice, this is actually our DC term. This thing doesn't really do much, DC term. It just shifts our graph. If you don't believe me, let's just make it a -1. And you see that the graph shouldn't change. Well, the magnitude changes, but that's the whole point of this. This is our DC term. These guys are our tuners. The higher the power, the more this thing will dominate the thing. It's very sensitive. If you make it too heavy, I'll show you this. If you put 3, look how heavy it gets. See it, like it completely inverts it, like by a lot too. See, just does a lot of things. 0.001. Oh. See that? But if you make it, like if you change it a little bit, like it starts affecting it a lot. So that's the whole point of assignment, the exercise 2. Exercise 2. So now you know how to do that. Use these functions right there. Now for this one, you're going to be doing, you're going to be touching the Generalized Fourier Series, the whole meat and cheese of this class. This is this. What are we supposed to do? Hilbert space, complete. Derive an expression for the exponential Fourier series for the following signals. Oh, okay, so we're using the C's. So what I want to try and show you for a little bit is, I'm not going to go super in depth. You'll have to do it for homework too. And how long are we in this video? I don't want to make it too long. It doesn't tell me. Oh, 20 minutes. All right, sweet. That's more than enough. I want to make this very quick. So the whole point of, so you're going to have new weights. I'm going to call it e to the, how do I want to explain this? Do I want to? Okay, let me just show you what I was trying to do. J2 pi n t. There we go. So we have a signal right here. We have C of n is equal to e to the j2 pi n t. But actually, this probably might be a future topic. But this is the whole main point of this. Is if you have a signal like this, actually, why I was hesitating a lot was because this is not good. This is for n is equal to 1 to capital N minus 1 plus C of 0, which is equal to the DC term, which is, well, 1. So the full Fourier projection, or the Fourier projection, I'm just going to call it FP of t, which is equal to this DC term, I'll call it DC, plus whatever these guys are. So, but the reason why I was hesitating is because there needs to be negative numbers. I'll show you. E to the j 2 pi of t minus or plus, plus e to the j minus 2 pi t divided by 2 plus e to the j 4 pi t plus e to the minus j 4 pi t for 2, and then dot 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 plus e to the j 2 pi of n minus 1 t plus e to the minus j 2 pi n minus 1 t. And I'm supposed to not show you this because this is the whole point of this class, and this is what makes me go crazy. I love this topic, where this right here is actually another way of writing cosine. Cosine of omega is equal to e to the j omega plus e to the minus j omega divided by 2. Like this right here is our exponential Fourier series. But why I say we group it like this is because our weight, I'm going to call it alpha 0, alpha 1, alpha 2, and then alpha n minus 1. These are our weights, remember, right? I'm not calling, well, they don't call it weights, but I'm thinking of them as weights. Like how much of this do we need? How much of this? And the more higher the power, or the faster, this right here is a fast signal. This right here, 2 pi t every period, or every 2 pi, well, it does a slow signal. Then this one's faster, and this one's even faster. So the higher your power, the more faster your signal. So I'll let you handle that information with care, and I think that's what he wants. I don't know. I'm not understanding this part. Consider Hilbert space H. Yeah, that's easy to know. The generalized Fourier series. Derive an expression for the exponential. Yeah, when I see exponential, I think of this. So basically everything what I'm trying to do is I think you're going to have to replace your basis set with this. But the thing you need to know is that if you're going to have, let's do this. If n is equal to 0, right? N is equal to 0, that's your n term. This is going to be your DC term. If you're going to have n is equal to 1, right? You need to you're going to have a signal here, but you also need to have another signal here. So that's because you can't have when you're having Euler equations like this, you need to have its conjugate pair in order for this to be real in the time domain. But let me just check what I do in the handy dandy solution manual, actually, because okay, we have this. Let me see something quick, because I want to make sure you guys know what's going on. Bear with me, bear with me. There we go. Oh yeah, so this is I'll just show you quick solutions, but this is what your projection is going to look like. See how this right there looks pretty clean, and then I'll show you oh, where'd it go? I'll show you again. There we go. The higher our powers, the more functions, the more it looks really nice. So if you can get this really nice thingy, then you should be fine. But the point is, you see this 5 right here? I have 5 or 15. You have to have 1, 2, 3, 4, but you have to double it. You have to have these guys right here. If not, you're gonna see bad numbers. So that's a warning to make sure don't do, like, if you just have these guys, that's wrong, because that means these become imaginary. You can't see them. To see them, you need to see the other side. So that's a tip that I want to make sure you guys know to generate this real-time signal. So, but I will show you the other way I wanted to show you, the cool way. And I created this little example right here. And let me close my marker. So let's figure it out right here. Why did I put this right there? Oh, there we go. So right here I create, so our exponential thingy, right? So 5, right? We're having 5 of these exponential signals. So I just created these exponential thingies. This is what I did. So I'm creating from -5 to 5 because I want the negative powers. So I just literally created a vector of, let me just run that right here. Because you can't post them in real time, that's the whole point. If I were to do, let me see if I can do the following for you. Figure 4 plot t, and then I want to add these two. This right here is speed of the fastest signal. Oh yeah. Look how fast that guy is. Oh, I found a pattern. Oh, there we go. No. Oh. This is all great information. I love this stuff. 2 and 10. So this blue one right here is that first signal. It's a slow one, or a really fast one. And then let me show you this. This might be my last one. Of 3. Actually, 5. What's the other guy? Mirrored 7. See, that's our slower signal. And let me just erase that. So that blue signal right there is that fastest signal because that's the highest power. And then this red signal is our slower one. And as we get closer to this DC term, like I split it. If you have I is equal to 0, this right here is going to be 0. Exponential of 0 is 1. So that's why I have this, but I mirrored it. So it's like 1, 2, 3, 4, 5. This is the negative speed, or the negative frequencies, the positive frequencies. I add those similar frequencies, and you get this function. If you add all these signals, you get this happy function from 0 to 1. And you'll probably see this. You see that? But to ignore it, don't worry. But you should be worried if your sum, let me show you sum. If your sum becomes, oh, that's interesting. Oh, maybe it's barking because of this. Yeah, who cares? Don't worry, you guys will be fine. But let me get to the whole point of this. And this is the final part before I close it. So right here is the same thing, and I created my own weights. And this right here is actually a, well, it's not too popular, but this is my own thing. This is 1 divided by 1, 1 divided by 3 times those speeds. And let me run this one. Let's get rid of that. And look at that, some weird functions, and you can do a lot with these. But the point is, these right here are weights that go to these speed thingies. And if you want to create your own thingies, like look at that. I'll put that away. Like, look at that. You can create a whole bunch of funny functions. Actually, let me put a -1 here. Oh, a minus. Like, look at that. Maybe you get another -2. Maybe a plus right here. Oh. See, you can create all these certain crazy functions. This doesn't have to be 9. Maybe let's make it 13. See, it looks pretty cool. 2. I want to see what this does. 8. See, really cool stuff. So that's the whole point of this assignment, to get you into it. Like, you can create any function using these basis functions. This is for n is equal to 5. Like, oh, but okay. But the point of this half is to make sure you double your signals. You have your DC term, which is n equals 0. This is 1, 2, 3, 4. But you can figure out an efficient way of doing that. So I wanted to show you that, and hopefully this is just informational. This is just to open your practical eyes. This is what practical engineers like to think about. But I think you should be okay. And we are at 32 minutes. Oh yeah, the cool thing about this is if you plot any of your exponential Fourier series for whichever signal, you can choose this one or this one. Oh, by the way, for this one, to generate this one, you need to use sine, as in sine. Let me show you. Sine of cosine, or I don't remember. Actually, no, sine of. Should you use sine? Yeah, just make sure it pulses. Just make sure it does this. You'll be fine. But a sine, actually, why was I saying sine? Where is it? SGN. Oh yeah, okay, that's how you create the square wave. But don't use SGN, you have to use SIGN. Because the new update for MATLAB changed it. This is all from 2009. So other than that, you guys should be set. And with that, good luck. That's my video. Oh. No, no, wait. No, no. I played Dr. Steve Rude's video. Wait. Closer. There you go. Woohoo! Alright. Take care.